Okay, kids, we've moved on into the next chapter. I know I haven't given you an assignment yet. Just be patient. I'm looking more at a kind of a unit thing as opposed to chapter by chapter. And we're moving on into magnetism. Now, if you're watching this video lesson without watching the first segment of the video that I asked you to watch, then this, what I'm going to be talking about to you right now, is going to be more difficult. It's really important that you had watched that video first. Okay, so I'm going to pause right now. This is my little dramatic pause. Watch the video. Okay, I'm back. I hope you watched that video. So magnetism, where did it start? Well, some historians say that magnetism was first discovered in an area called Magnesia around 600 before the Common Era. But who knows? I mean, you could have had someone in Africa, South America, Asia, North America discovered it before that. It just wasn't documented. This is documented Western history, so take it as it is. And it's in was in Greece today, Turkey, and they found this iron mineral called lodestone. Lodestone, Lode, stone. And they found that it attracted iron. Well, someone in our modern era that would see this would call this ferromagnetism because it's attracting iron, and Latin for iron is ferro, like the symbol on the periodic table, Fe, okay? And they did some more experimenting with this lodestone that they found, and they found that one end, or you can call an end a pole, always point north. One end of it always pointed north. So when they started to get hunks or samples of this, they said, well, this end always points north. That's called the north seeking pole. This end always points south. That's the south seeking pole. Now, in our modern era, a piece of lodestone or this magnetic material would be called a bar magnet. That's what it would be called. So, as they were thinking about this, uh, that one end pointed north, they came to realize that there must be some type of magnetic field, and the symbol for magnetic field is B with an arrow hat. So it's definitely a vector thing, right? With the whole idea of direction, right? Because things are pointing in a certain direction. So it's a vector field. And you've seen vector fields before, electric field, gravitational field. And there has to be then some magnetism associated with the Earth, and there is. And in our modern language, we would call this geo from Earth. Geo means Earth. Geomagnetism. Now, the Earth has a very strong magnetic field, very strong B, and there's a geographic north and south. So let me show you in this picture here. So here's the North Pole and there's the South Pole. And these are what we call geographic poles because of latitude and longitude and things like that. All right. But slightly off of them is the magnetic poles of the Earth. Now, if you think about this, the magnetic poles of the Earth operate like this. We have geographic north and then a magnetic south. Geographic south and then a magnetic north. And then what I've drawn for you here are field lines in yellow, magnetic field lines. And it's a magnetic field, so it's got a direction. And it is understood that a magnetic field line always leaves the north and then enters the south. Magnetic field lines leave the north and enter the south. Magnetic field lines leave the north and enter the south. Now these poles, they're not stuck there like the geographic poles are. They wander about. They move around through the centuries. So keep that in mind. And also the strength of the Earth's magnetic field goes through cycles that can be hundreds of thousands of years old, or long, I should say. And sometimes, and it's many times, I should say, the Earth's magnetic field will weaken and then reemerge with north and south flipped in the other direction. So that's also been documented in our geological history. As a matter of fact, as we speak, there's a huge weakening of the Earth's magnetic field in the South Atlantic Ocean between Africa and South America. There's a weakening there. So next, I've drawn another picture for you here. So here's the geographic North Pole, the geographic South Pole. Here are our magnetic poles here and here. And if you get a compass, and a compass is a way of measuring a magnetic field. When I was a kid, they used to teach you how to use compasses so you wouldn't get lost. Now you just use the GPS on your phone. Let's say we're right here. This little dot here is NFO, Niagara Falls, Ontario. Your compass would point towards the magnetic North Pole. It wouldn't point towards the geographic North Pole. And so there's a difference of angle between those two directions, and that is known as the angle of declination. Also, if you look at the magnetic field lines that leave the surface of the Earth and then enter the surface of the Earth somewhere else, so let's pick this magnetic field line right here. I can come up with another angle. I can draw a line that takes its direction from the surface of the Earth, and at that same spot I can draw a line that takes its direction from the magnetic field line that would leave the Earth, okay, and then enter the Earth somewhere else. See how that's happening? Well, that angle right here is called an angle of inclination. And don't be too spooked by B, the magnetic field, okay? It is measured by a compass. You put a little compass, and a compass is just a small, tiny magnet that's allowed to spin. That's all it is. Probably saw that in video. So don't be afraid by this new field called magnetic field, because it's very similar to things we've looked at in the past, an electric field, which is measured by a small positive test charge, or a gravitational field that's measured by a small test mass. So between the video you watched, this little short video lesson, and the reading and questions I've asked you to answer, this will be our introduction to magnetic fields and magnetism in general. Okay, have a great day. Bye-bye.